All right, so we're going to go ahead and start chapter 5. So the first lesson we're going to look at in chapter 5 deals with extrema on an interval. So we're going to take a look at how we find absolute maximums and absolute minimums of a function on a closed interval. Okay, so to start with, we're going to do look at a couple of definitions. So the first one says that a function f has an absolute or global maximum. Okay, so those are both synonyms. Just to let you guys know, I always call them absolute maximums and absolute minimums. Okay, so a function f has an absolute maximum at x is equal to c if and only if f of c is greater than or equal to f of x for all x in the domain of f. Okay, similarly, f has an absolute or global minimum at x is equal to c if and only if f of c is less than or equal to f of x for all x in the domain of f. Okay, now the most important thing in this lesson, okay, is the extreme values theorem, which says that if the function f is continuous on the closed interval from a to b, then f attains an absolute maximum and an absolute minimum on that closed interval. Okay, so if your function is continuous on a closed interval, then your function has to have an absolute maximum and an absolute minimum on that closed interval. So what we want to do is we want to take a look at how do we go about finding where the absolute maximum, where the absolute minimum occur? Okay, so the first thing we want to look at is something called Fermats Theorem. And Fermats Theorem states if f has a local minimum or a local maximum at x is equal to c and f prime of c exists, then f prime of c has to be equal to 0. Okay, so if you guys remember, I'm just going to talk about local maximums. You can make the same argument for local minimums. Okay, so a local maximum, if you guys remember back in chapter 1, we defined a local maximum, and we're going to talk more about this later on in chapter 5. We said that a local maximum is where a function changes from increasing to decreasing. Okay, so if you look at the two graphs that I've drawn down below, the local maximum for both of these functions is going to occur at the point in blue. Okay, so if you look at that first graph, you have that curve opening downward. And if you look at the slope of your graph at that point in blue, your graph has a horizontal tangent at that point. Okay, so what Fermat's theorem says is that if your function, again, we're just going to talk about a local max, and you can make the same argument for a local minimum, but if your function has a local maximum at x is equal to c and f prime of c exists, then f prime of c has to be equal to 0. Now, the other way we can have a local max is if you look to the graph over to the right, okay? So sort of looks like an absolute value graph that's opening downward. And when you look at that point in blue, that point is also a local max because our function goes from increasing to decreasing at that point. However, when you look at the slope of your graph at that point, the derivative is going to be undefined at that point because your graph has a corner. Okay, so again, if you recall back into the lesson, I think it was 4-1, we said that there were 4 instances where a function fails to be differentiable. The first one is a corner. The second is a cusp. The third is a vertical tangent. And the fourth one is a discontinuous point. Okay, so if your graph is going to have a local min or a local max, then that means that the derivative either is equal to 0 at that point, or the derivative is not going to exist at that point. Okay, so the next term that you are going to see us define, you guys are going to hear pop up a ton in chapter 5. Okay, a critical number, or what I call them critical points. Okay, so a critical number or a critical point of a function f is a number c in the domain of f where either f prime of c is equal to 0 or f prime of c does not exist. Okay, so when you're asked to find critical points, you are asked to find where your derivative is equal to 0 or where the derivative does not exist. So when it comes to finding absolute mins and absolute maxes of a function on a closed interval, you have to check 3 things. Okay, number 1, you have to check where the derivative is equal to 0. Secondly, you have to check where the derivative does not exist. Okay, and 1 and 2, again, those are the critical points. That's where the derivative is equal to 0 or where the derivative is undefined. Okay, the third thing you have to test to check for absolute mins and absolute maxes are the endpoints of the interval. So your absolute max and absolute min are either going to occur at the critical points or the endpoints of the closed interval that is given. Okay, so let's get into some examples illustrating this extreme values theorem. So the directions ask us to find the critical points and determine the absolute max and the absolute min of the function on the given interval. All right, and for number 1, we are given the function f of x, which is equal to 2x plus 1. We're looking at this on the closed interval from 0 to 4. Okay, so the first thing you have to check is you have to check and see if you can even use the extreme values theorem. So we have to check to make sure that our function is continuous on the interval that's provided. So the way that we check for continuity is we just want to find the domain of our function, and if our function is defined everywhere on the interval that is provided, then it is continuous everywhere on that interval. So when we look at number 1, the function f of x is equal to 2x plus 1. That function is linear, which makes it a polynomial. We know the domain of a polynomial function is all real, so that polynomial function is defined everywhere, thereby making it defined on the closed interval from 0 to 4, and therefore it is continuous on that closed interval. Okay, so what we want to do is we want to take the derivative of this function. So f prime of x, the derivative of 2x plus 1 is 2. And we want to take that derivative and find the critical points. So we are trying to find, when we are finding critical points, where the derivative is equal to 0 or where the derivative does not exist. And that derivative is never going to be equal to 0. And also that derivative always exists. So this function here has no critical points. So what we have to do then is we have to just test the function value at the 2 endpoints. Whatever one is the largest is the absolute max. Whatever one is the smallest is the absolute min. So when we input 0 into our function, 2 times 0 plus 1 is 1. When I input 4 into the function, 2 times 4 is 8, plus 1 is 9. Okay, so 1 is the smallest value, that is the absolute min. 9 is the biggest value, that is the absolute max. And what I'm going to do for this example and the next example is I'm going to sketch the graph on the given interval, and we can actually check to see that we find the correct absolute min and absolute max. Okay, so if I want to sketch the graph of this function, So if we look at 2x plus 1, that has a y-intercept of 1 and a slope of 2. So if we look at that graph on the interval from 0 to 4, the smallest value on that graph is at the point 0, 1. So you can either write the absolute min as an ordered pair, or you can write it in function notation. Okay, either one of those are acceptable. I typically, whenever I write these, I write them in function notation. Okay, so I would write the absolute min as f of 0 is equal to 1, the absolute max as f of 4, which is equal to 9. Okay, let's do number 2 together. So for number 2, we're given the function f of x equal to x squared on the closed interval from -1 to 3. Okay, so again, first thing we want to check, can we use the extreme values theorem? So is that function continuous on the closed interval from -1 to 3? And the answer is yes. X squared is a polynomial. It's defined everywhere. It's continuous everywhere, thereby making it continuous on the interval that is provided. All right, so what I want to do next is I want to find the derivative of my function. So the derivative of that function is equal to 2x. There is nowhere for which that derivative is undefined. Okay, so to find the critical points, we want to find where that derivative is equal to 0, and that happens when x is equal to 0. Okay, so we have 3 values that we have to test now. We have to test f's value at -1, the first endpoint. I have to test f's value at 0, the critical point, and then we also test f's value at 3, which is the the second endpoint. So when I plug all of those values into my original function, -1 squared is 1, 0 squared is 0, 3 squared is 9. 0 is the smallest value, so that is the absolute min. 9 is the largest value, that is the absolute max. And if we sketched a graph of this function on the interval from -1 to 3, so graphically this function would look like this. If we graphed x squared, it would look like so. So just as we found, this value, this point here in purple, is the smallest value on the graph. That's the absolute min. That point in purple is the largest value on the graph. That is the absolute max. Okay, so I'm not going to graph any more of these, but I'm just showing you graphically, like that confirms what we did using calculus and algebra. Okay, so same idea. I want you guys to try 3 and 4. So find the absolute min and absolute max of that function on the given interval. So go ahead and pause the video to work on that. All right, so when we look at number 3, again, we have a polynomial function whose domain is all real, so it's continuous everywhere, thereby making it continuous on the closed interval from -2 to 2. All right, so we're going to take the derivative of this function to find the critical points. So the derivative is 3x squared plus 2x minus 1. Again, because that derivative is a polynomial, that derivative is defined everywhere. So our only critical points are going to be where the derivative is equal to 0. Okay, so I can factor that quadratic function. That's going to factor to 3x plus 1, or sorry, 3x minus 1 times x plus 1. So our critical points here are going to be when x is equal to 1/3 and when x is equal to -1. Okay, so we have 4 values that we have to test. We have to test f at the starting point, -2, f at the critical point, -1, We have to test f at the other critical point of 1/3, and then we have to test f's value at the endpoint of 2. So when we plug all of those values into our function, like I'm not going to work through the algebra of this. It's just like computational math. So f of -2 is -2, f of -1 is 1, f of 1/3 is -5/27, and f of 2 is equal to 10. So -2 is the smallest value, that is the absolute min. 10 is the largest value, that is the absolute max. All right. So same idea with number 4. Now number 4, we have a rational function, so we have to look at this a little bit more closely. So we know our denominator cannot be equal to 0. But when we look at our denominator, it is x squared plus 4. That's never going to be equal to 0. So the domain of that function is all real numbers, thereby making it continuous everywhere and continuous on the closed interval from -3 to 4. So we can use the extreme values theorem for the function on the given interval. Okay, so we want to find the critical points. So we're going to take the derivative of this function using quotient rule. So the derivative is going to be low, d high, derivative of the top function is 2x, minus high, d low, the derivative of the bottom function is 2x, all over low, which is x squared plus 4 quantity squared. Okay, so I want to clean up that numerator. So when I distribute 2x over the first two terms, we get 2x cubed plus 2x times 4, which is 8x. And then I'm going to distribute -2x across the next two terms. So that's minus 2x cubed plus 8x all over x squared plus 4 quantity squared, which is going to make f prime here equal to the 2x cubes cancel, so 8x and 8x make 16x over x squared plus 4 quantity squared. Okay, so we have something different here. Our derivative is in the form of a fraction. So if you look at a fraction is going to be equal to 0 when the numerator is 0. So that means that our critical point here is at x is equal to 0. And this fraction also may be undefined. That's going to happen when the denominator is 0. But our denominator here is never going to be 0. Okay, so our derivative is never going to be undefined. All right, so our only critical point is at x is equal to 0. So we're going to test the function values at -3, the critical point 0, and the other endpoint of 4. And when we evaluate at -3, we get 5/13. When we evaluate at 0, we get -1. When we evaluate at 4, we get 3/5. Okay, so very clear what the smallest value is. It's -1, so that is our absolute min. Now, the largest value, you can find it one of two ways. Like if you want to give 5/13 and 3/5 a common denominator of 65, and then figure out which is the bigger numerator, you can do that, and that's fine, okay? But I'm going to do something a little bit quicker. I can look at 5/13 and tell that that number is smaller than 1/2. When I look at 3/5 is bigger than 1/2. So that is the bigger number. That is our absolute max here. Okay, you guys try 5 and 6. So for 5, you have the function f of t equal to the cube root of t times 8 minus t on the closed interval from 0 to 8. And for 6, you have f of x equal to x minus 4x over x plus 1 on the closed interval from 0 to 3. All right, find the absolute max and absolute min for those functions on the given interval. So again, pause the video and give those two a try. Okay, So let's see how we did with these. So when I look at number 5, I want to check the domain of that function first. So the domain of the cube root function is all reals. The domain of the polynomial 8 minus t is also all reals. So the domain of that product has to be all reals as well. So that function is continuous everywhere, thereby making it continuous on the closed interval from 0 to 8. Now you have two ways that you can proceed with this. If you want to use product rule to differentiate, that's fine. What I'm going to do instead is I'm going to rewrite the cube root of t as t to the 1/3 power, and then distribute t to the 1/3 power across both of those terms. Okay, so that's going to give me 8t to the 1/3 power minus t to the 4/3 power. And I'm going to use power rule to differentiate. Okay, you should get the same result however you do it. Okay, so I can pull 8 out front. The derivative of t to the 1/3 power is 1/3 t raised to the negative 2/3 power minus the derivative of t to the 4/3 power is going to be 4/3 t to the 1/3 power. Okay, so what I'm going to recommend that you guys do is to rewrite this entire expression here, this entire derivative, back in the form of a radical. Okay, so when I do that for the first quantity, the only thing we have left in our numerator is 8. Our denominator is going to be 3 times the cube root of t squared. Okay, minus, when I rewrite the next quantity in terms of a radical, we have 4 times the cube root of t all over 3. Okay, so when I look at the two fractions, like my goal is to combine into a single fraction. I want to get a common denominator, and the common denominator is going to be 3 times the cube root of t squared. So when I look at my fraction on the left, it already has that denominator, so I don't have to do anything to that first numerator. But if I want the second fraction to have that denominator, I have to multiply the top and bottom by the cube root of t squared. So when I do that, up on top, when I multiply these two things, that gives me 4 times the cube root of t cubed, and the cube root of t cubed is t. So that becomes 8 minus 4t. And I'm almost done simplifying this. All I have to do now is factor a 4 out of the numerator. And when I do so, that gives me 2 minus t over 3 times the cube root of t squared. Okay, so we want to find the critical points for this. So critical points are going to be where the derivative is equal to 0. So since this is a derivative in fraction form, the fraction is going to be 0 when the numerator is 0, and that happens when t is equal to 2. And we also want to find where the derivative is undefined. The derivative is going to be undefined when our denominator is 0. And our denominator is going to be 0 when t is equal to 0. Okay? So the good news for us is this critical point at t is equal to 0 also happens to be the endpoint for our interval. So we only have 3 things that we have to test. We have to test f's value at 0, f's value at 2, and f's value at 8. So when we plug 0 into the function, we get 0 as an output. When we plug 2 into the function, it's going to give us 6 times the cube root of 2. And when we plug 8 into the function, it gives us 0 as an output. Okay, so 6 times the cube root of 2, that's the biggest value, that is the absolute max. And 0 is the smallest value, it is the absolute min. It just so happens that our graph has 2 absolute mins. Has one at the point 0, 0, and also has one at the point 8, 0. Okay, let's move on to the next one. So when we look at 6, we have a rational function here. So our function, like -1, is not in the domain of our function. So our function is not continuous at -1, but -1 is not on the interval from 0 to 3. So our function is continuous everywhere on that interval, which means we can use the extreme values theorem. Now you have two ways that you can take the derivative of number 6. Like if you want to combine x and 4x over x plus 1 into a single fraction and take the derivative that way, that works fine, okay? I'm not going to do it that way. I'm just going to take the derivative the way that it's written. You should get the same thing either way, okay? So the derivative of x is 1 minus, and then I'm going to use quotient rule to take the derivative of 4x over x plus 1. So that's going to be low. D high, the derivative of the top function is 4, minus high. D low, the derivative of the bottom function is 1, all over low, which is x plus 1 squared. Okay, so f prime here is going to be 1 minus, when I distribute 4 across both terms, we get 4x plus 4 minus 4x all over x plus 1 squared. And then the 4x and negative 4x, like they cancel. So that's going to give me f prime equal to 1 minus 4 over x plus 1 squared. Okay, so just like in the previous example, I want to combine into a single fraction here to simplify. Okay, so my common denominator is going to be x plus 1 squared. So 1 is x plus 1 squared over x plus 1 squared minus, and then the second fraction I don't have to do anything to because it already has that denominator. So I'm going to subtract 4. Okay, so I'm just going to simplify the numerator here. So x plus 1 squared is x squared plus 2x plus 1 minus 4 over x plus 1 squared. And then that's going to make f prime equal to x squared plus 2x minus 3 over x plus 1 squared. And then I can factor the numerator. That numerator is going to factor to x plus 3 times x minus 1 over x plus 1 squared. Okay, so we want to determine the critical points here. So our derivative is going to be equal to 0 when the numerator is 0. So that happens when x is equal to -3 and x is equal to 1. And we're also going to have critical points where our derivative is undefined. So that happens when our denominator is 0. So that happens when x is equal to -1. Now, when I look at the critical points relative to the interval that we're given, so we're given the interval from 0 to 3, this first critical point of -3 does not lie on that interval. So I don't have to test that. Nor does the critical point at x is equal to -1. So I don't have to test that either. Okay? So the only values I have to test here are f's value at the starting point 0, f's value at the critical point that's on that interval 1, and f's value at the ending point 3. So when I plug in 0 for x, we get 0 minus 0 over 1, so that's 0 minus 0, which is 0. When I plug in 1, we get 1 minus 4 over 2, which is 1 minus 2, which is -1. And when we plug in 3, we get 3 minus 12 over 4, which is 3 minus 3, which is 0. Okay, so -1 is clearly the smallest value. That is our absolute min. And 0 is the biggest value, so this happens to have 2 absolute maxes. Okay, last example. So the directions for the last one only ask us to find the critical points of the function f. Okay, so again, we just have to find the critical points here. We're not finding the absolute max and the absolute min. So we have f of x equal to x squared times the cube root of 2 plus x. Okay, so the cube root of 2 plus x, that is like saying 2 plus x raised to the 1/3 power. So I'm going to use product rule to differentiate. So f prime is going to be the derivative of the first function, which is 2x, times the second function, which is the cube root of 2 plus x, plus the first function, x squared, times the derivative of the second function. So for me to take the derivative of the second function here, it's a composite function, I have to use chain rule. So that's the derivative of the outer function, which is 1/3 something to the negative 2/3 power. We evaluate that at the inner function, 2 plus x, and then we multiply that by the derivative of the inner function. The derivative of 2 plus x is just going to be 1. Okay, so again, I want to rewrite this back in the form of a radical. Okay, so f prime is 2x times the cube root of 2 plus x plus, when I multiply all this stuff out, the only thing we're going to be left with in the numerator is x squared. Our denominator is going to be 3 times the cube root of 2 plus x squared. Okay, and again, I want to combine this into a single fraction. Okay, so that's going to make f prime equal, my common denominator here is going to be 3 times the cube root of 2 plus x squared. Okay, well, when I look at that first quantity, that's like writing that over the number 1. So to get that common denominator, I have to multiply the numerator and denominator by 3 times the cube root of 2 plus x squared. So when I multiply 2x times 3, that gives me 6x. And then we have the cube root of 2 plus x times the cube root of 2 plus x squared, which is going to make the cube root of 2 plus x cubed, which is 2 plus x. The second fraction already has that denominator, so I don't have to do anything to that second fraction. Okay, I leave that numerator alone. Okay, so all I have to do now is distribute 6x across both terms. So that's going to give me 12x plus 6x squared plus x squared. So if you guys don't mind, I'm just going to combine that into making 7x squared. All over 3 times the cube root of 2 plus x squared. And then all I need to do now is factor an x out of the numerator, which leaves me with 12 plus 7x over 3 times the cube root of 2 plus x squared. Okay, so critical points are going to be where the derivative is 0, so that happens when the numerator is 0. So that occurs when x is equal to 0, or when x is equal to negative 12 over 7. And then our derivative is undefined where the denominator is 0, and that's going to happen when x is equal to negative 2. Okay, so that right there is how you find the critical points for that function. Okay, so that'll wrap up the first section of chapter 5. There will be one more video that I will post probably tomorrow looking at the second section of chapter 5. All right, so hope you guys have a great Thanksgiving break, and we'll see you in class next week. Take care, everybody.